Hey everyone, welcome back to Chem Story. Today, let's talk about cyclohexane, one of the most important cyclic compounds in organic chemistry. You might already know that ring strain can make some cyclic compounds unstable. But did you know that cyclohexane has almost no ring strain at all? Unlike smaller rings like cyclopropane and cyclobutane, which deal with a lot of built-in strain, cyclohexane adopts a unique three-dimensional shape that eliminates that strain. And that's what makes it so incredibly stable. In this lesson, we'll explore the structure of cyclohexane, take a close look at its chair conformation, and learn how to visualize it using Newman projections. We'll also talk about ring flipping, a key idea that helps explain why cyclohexane is constantly shifting between different forms. Let's get started. One of the key reasons cyclohexane is so stable is that it has zero ring strain, its total strain energy is 0 kilojoules per mole. That's because its bond angles are 109.5 degrees, which is exactly the same as the ideal angle for sp3 hybridized carbon atoms in an acyclic alkane. That means there's no angle strain. And on top of that, in its most stable form, all of its CH bonds are staggered, which gets rid of torsional strain as well. Instead of being a flat hexagon, cyclohexane naturally folds into a three-dimensional shape. The most stable and most common form is called the chair conformation. This shape helps minimize strain by keeping the bond angles close to ideal while also putting all the hydrogen atoms in a staggered arrangement. The chair conformation gets its name because when you look at it from the right angle, it actually looks like a little lounge chair. In this shape, the bond angles stay right at 109.5 degrees and all the CH bonds are staggered. And that's what makes cyclohexane so incredibly stable. If you check out the chair forms in the image, you'll see that 4 of the carbon atoms lie in the same plane, forming the seat of the chair. One carbon is pushed upward like a backrest, and another is pulled downward like a footrest. That specific shape helps eliminate ring strain and adds to the molecule's overall stability. Now, cyclohexane can be drawn in a couple different ways, but they all represent the same chair conformation, just from different viewing angles. In the chair conformation, each carbon in the ring has 2 different types of hydrogens or substituents, and the difference is all about their orientation. Some point straight up or straight down, parallel to the imaginary vertical axis of the ring. These are called axial positions. Others stick out more to the side, roughly in the plane of the ring, angled away from the center. These are called equatorial positions. In the diagram, you'll see the axial hydrogens shown in green and the equatorial ones in orange. This alternating pattern of axial and equatorial positions plays a big role in keeping cyclohexane stable. It helps minimize steric strain and keeps the molecule in its most relaxed form. We can also use Newman projections to get a better understanding of the chair form of cyclohexane. Instead of looking at the molecule from the side, we look straight down a carbon-carbon bond, just like we do when analyzing bond rotations in open-chain alkanes. This view makes it much easier to see how the axial and equatorial positions are arranged. Newman projections are usually used to compare staggered and eclipsed conformations in alkanes, but they're also super helpful when it comes to visualizing the three-dimensional shape of cyclohexane. When we look at the chair form from different angles, we can actually draw 2 distinct Newman projections. The chair form can be viewed from 6 directions, and each Newman projection corresponds to 3 of those views. In the 3D image, the axial positions are marked in green, and the equatorial positions are marked in orange, which helps you easily tell them apart. The 3D model gives you a clear idea of how everything is positioned in space, while the 2 Newman projections on the right show you what the chair form looks like from 2 different perspectives. If you follow the orange arrow shown in the structure, you'll end up with a Newman projection where the front carbon substituents form a Y shape. One bond points straight down, and the other 2 angle upward. Meanwhile, the back carbon substituents stay staggered, which helps maintain the overall stability of the molecule. If you follow the yellow arrow shown in the structure, you'll see a different Newman projection where the front carbon substituents form an inverted Y shape. Even though these 2 projections might look different at first, they actually represent the same chair form of cyclohexane, just viewed from different angles. This idea becomes really useful later on when we start analyzing things like ring flips, steric interactions, and substituent preferences, which we'll dive into in more detail soon. Cyclohexane's chair form isn't stuck in one shape. It's constantly shifting through a process called ring flipping, where the structure temporarily moves through other conformations before settling into a new chair form. This natural movement helps the molecule adjust its shape, so bulky substituents can move into more stable equatorial positions, which reduces steric strain. Now, during a ring flip, there are two important things to remember. First, the up and down positions don't change. If a hydrogen or substituent starts in the up position, it stays up. If it starts in the down position, it stays down. Second, the axial and equatorial positions switch. Any group that was in an axial position moves to an equatorial one, and vice versa. You can clearly see this transformation in the image. On the left, the yellow-labeled hydrogens are in axial positions, and the blue-labeled hydrogens are in equatorial positions. After the ring flip, they've swapped. The yellow hydrogens are now equatorial, and the blue ones are now axial. Even though the shape looks different after the flip, it's still the same cyclohexane molecule. The only thing that's changed is the orientation of axial and equatorial groups. We can also apply the idea of a ring flip to Newman projections. Instead of looking at the chair form from the side, we now look straight down a carbon-carbon bond, just like we do with regular Newman projections. This view makes it super clear how substituent positions shift during a ring flip. In the image, you can see that transformation really clearly. Just like in the regular chair form, axial and equatorial positions switch. If a substituent starts off in an axial position, it moves to an equatorial position after the flip, and vice versa. But remember, the up and down orientations stay the same. Only the axial and equatorial positions are changing. So even though the projection looks different, it's still the same cyclohexane, just with the axial and equatorial groups swapped. Seeing a ring flip through Newman projections really reinforces a key idea. Chair forms aren't static. They're constantly switching between two equally stable shapes. And that also tells us something important. Axial and equatorial positions are interchangeable, which becomes especially useful when we analyze substituted cyclohexane molecules. And that's it. To sum it up, cyclohexane is unique because it has zero ring strain thanks to its chair conformation, which helps it avoid both angle strain and torsional strain. We looked at how Newman projections help us visualize the chair form and how ring flipping swaps axial and equatorial positions while keeping the overall shape of the molecule intact. Thanks for watching, and I'll see you in the next video.